In memory, there are usually many processes. There are only a very small number of CPUs. For example, here is only one. Then, every time, the CPU needs to decide which process to run next. This selection job is called the CPU scheduler. Of course, if there are multiple threads in a process, threads managed by the kernel are based on threads instead of processes. We assume here that there is only one thread in the process, so the process is the base unit. So first of all, there are usually two kinds of processes. One is to occupy the CPU for a long time for calculation, which is called computational intensive. There is another type. The CPU calculation time is short, but the time to access external devices such as the disk is long, and the number of times is large, which is called I/O intensive. I/O here is shorthand for input and output. In fact, as the calculation speed of the chip becomes faster and faster, the read and write speed of the disk is relatively slow. Therefore, the number of I/O intensive processes is increasing. Now, more consideration is given to optimizing I/O intensive processes. For example, the emerging of Node.js is to deal with such scenarios. Therefore, different scenarios require different scheduling strategies. We can roughly divide the specific environment into three categories. The first is batch processing, such as bank interest calculation. Insurance companies need to process claims, and shopping malls need to process inventory lists. For this type, the simplest scheduling method is first come, first serve. For example, here process 1 runs first until it blocks. Process 2 continues to run. After the process 1 is ready, it will be queued to the end. However, this approach is obviously problematic. Suppose process 2 is computationally intensive and process 3 is I/O intensive. Then, if the CPU serves process 3 first, it will quickly let it out for I/O processing. But now process 2 has been occupying the CPU and process 3 has been waiting. So the overall efficiency is relatively low. With the previous lessons, the second algorithm is the shortest job first. That is, whoever has short calculation time will come first. For example, we can predict how long each process will occupy the CPU. Then, in this case, the I/O intensive process will be in the front, and the computationally intensive process will be in the back. If the CPU has been running a computationally intensive process for 7 minutes, there is still 1 minute left. Now there are I/O intensive processes coming one after another. Although it is shorter than the total time of a computationally intensive process, isn't it more reasonable to compare the remaining time? In this way, the algorithm is updated to give priority to the shortest remaining time. Let's talk about the second category, interactive. When a user needs to interact with the computer usually has many processes. For example, when the user is writing email, during this time, some handle email reception, some handle mouse signals, some receive keyboard signals, and some are responsible for the rendering of graphical interface, and so on. Obviously, they need to be performed at the same time. So the CPU can only be executed in turn, which is called round-robin scheduling. The time to execute one process at a time is called a time slice. The time slice cannot be too short because the process switching needs to be processed from user mode to kernel mode and then back to user mode. It takes about 1 million seconds, but it can be too long. Therefore, the time slice is usually between 20 milliseconds and 50 milliseconds. This is still not good enough because the importance of different processes is different. Here, obviously, the process B, C, and D that interact with the user are more important, while the background process A is relatively less important. The differentiated algorithm is called priority scheduling. According to the importance, the process is divided into 4 priority levels. The top is the most important, and the bottom is the least important. Then, process A as background processing is the least important. Process B and process C accept the user's instruction more important. Process D is responsible for the rendering, and the human eyes are very sensitive, so it is the most important. Now, the CPU always executes the high priority, so process D is executed. But if the priority is always this way, the remaining processes can only wait for process D to complete. Therefore, we still need time slice rotation. For example, now we can let process D execute a time slice first, and then reduce the priority of process D by one value to the end of priority 3. Because priority 4 has no process anymore, therefore priority 3 is the highest priority, and process B is executed. After process B is executed, it is downgraded to level 2. The CPU executes the process C, and then it also degrades, and so on. Then the priority here is only relative, and then downgrading from priority 1 can be priority 0, and continue on. Finally, there is the third type of environment, real-time systems. For example, video streaming, automatic driving system. Punctuality is more important than character operation. In the future, we will talk about multimedia technology, which including this content.